Hello, everyone. You are welcome to this lecture on differential equations. This is Math 350. My name is Joseph. I would take you through a couple of things as an introduction. I'll give you a motivation for differential equations. We'll look at classifications and terminologies that are often used when studying differential equations. And then we'll look at what we mean by the solution of a differential equation. Okay. How do you verify that a given function is actually a solution of a differential equation? And then I'll end with some applications. There are a gazillion probably applications of differential equations. I'll just mention a few of them as a way of motivation. All right. So differential equations often arise in trying to develop, if you like, mathematical models, okay, equations to describe or to study a particular phenomenon, a physical phenomenon. So for instance, if you want to know how an unknown function phi is changing as with respect to another variable, say t, you can call it time, then the equation that arises is often a differential equation. So in essence, a differential equation is an equation involving the rate of change of some quantity, right? So it involves a function and its derivatives. If I want to know how phi is changing with time, for instance, I need to find the derivative of phi with respect to time. How it's changing with space, say x, how you need to find the phi, the x, and so on. So it's one that involves the rate of change, if you like, of a quantity. So a simple example of a differential equation is what I've written here. Assume that you want to model the population of mosquitoes in a certain village. Then you could represent it by something like this. The change in the population of mosquitoes, let's call it M, with respect to time, is equal to K times M. In other words, we are saying that the rate of change is proportional to the amount or the population of mosquitoes, where K here is the, if you like, the constant of proportionality. So K is some constant that is known either from experiments or some observations. So you know K. So the point is that how do you find M and be able to predict the population of mosquitoes at a future time? Okay, so that is often the idea for predictive purposes. Okay, so so this is what I just mentioned, that how can we predict the population of mosquitoes at a future time? So for us, the given equation, if you like, this equation here is so simple that we can actually solve it directly. That is often not the case for most differential equations. So we can solve it, divide through by m, then we can have an equation that looks like this, the m over m is equal to k dt. Then I can integrate both sides, right? If you remember calculus, if I have the x over x, I mean, we know this, the solution is ln x. So in this case, it is ln m, which is equal to kt. K is a constant. So kt plus some constant. Then you can solve for m, right? Solve for m as a function of t, and you have this equation here where this c is some positive constant, okay? So m is given by this, which means that if I know what c is and I know what k is, I can project the population of mosquitoes given any time, right? In the future, as t goes to infinity, for instance, I can determine how this function behaves, okay? Now, that constant c there can often be determined if you know the population at a particular time, often let's say an initial time. If you know the population of mosquitoes, then you can determine the c. By doing that, then we can then use this equation 2, to help us predict the population of mosquitoes at some other time, okay? So for instance, okay, so this is just an example. Suppose that k is -5, which we know from some experiments or observations. And if initially at, for instance, time equals 0, the population of mosquitoes is, say, 1 million in your village, all right, or your city, town. Then we put in t is 0, this guy becomes 1, right? E to the 0 will be 1. C will be equal to m is 1 million, 10 to the 10 to the 6. So we know C. Okay, so that's what I've done here. So we know C, we plug it back into the equation. So M is given by 10 to the 6 e to the negative 5t. So using this, we can project the population at a future time. In this case, because the k is negative, as t goes to infinity, we know that the population will keep decreasing, right? It will keep decreasing exponentially. Okay, good. A couple of remarks about this. So what you should note is that the solution to a differential equation is not a constant, right? Like you solve a quadratic equation and you have x equals 2 or 1, right? The solution to a differential equation is actually a function, and that function often contains some arbitrary constant, like the c in our equation there. So now, because of those arbitrary constants, it implies that generally differential equations don't have unique solutions, all right? That's because if you pick, for instance, this is our solution, right? So this is often called a general solution because for every value of c here, you have a different solution, right? So there are, if you like, a multiple of solutions, an infinite number of solutions here, all right, that you can pick from. So in general, there is no unique solution. So equations like equation 2 are often called a general solution because they are general, they are not specific or particular. Okay, since there are infinitely many of them, there is a solution for every c. Okay, so here is an example using our solution, equation 2. Okay, so suppose that at t equals 0, c is 1. Okay, then for all future times, if this is where I'm starting from for all future times, my population of mosquitoes is going to decrease exponentially. If I'm starting from here, if at t is equals to 0, my m is 2, then I know c, right? So I can follow this line here to project the population of mosquitoes at different times. The same thing for this one. So you see that for each c, you're going to have several of these solutions. Okay, so one of them will be a particular solution. For instance, if I pick this one, then that will be a particular solution to the differential equation. Okay, good. So that was basically an introduction to differential equations, and if you like, a motivation. I'll say a bit more about motivation when I talk about the different applications. Now we want to look at certain terminologies or classifications of differential equations. Okay, so the unknown function in a differential equation, let's say the m in our equation, is called a dependent variable, right? It is a variable that is changing with respect to some other variable, right? So, and the other variable, which is t in our case, will be called the independent variable. So this is the variable that is not changing. So often it is clear from the equation which one is dependent and which one is not. So if I'm finding the y, the x, then the y there will be the dependent variable because it depends on how x is changing, right? I'm finding y with respect to changing, how y is changing with respect to x, okay? If I'm finding the m, the t, then m is the dependent variable and t is the independent. So often from the equation, you can tell which one is dependent and which one is independent. Okay, now another classification is that there's a difference between what is called an ordinary differential equation, or ODE, and a partial differential equation. Ordinary differential equation is a differential equation in which only the derivatives of the unknown function, right, let's say m, with respect to one independent variable appears in the equation. Okay, I'll give an example of that. So if I'm finding only the m dt and there is no the m, the x, or the m, the y in the equation, right? So I'm finding how m is changing with respect to only one variable, say t, then I have an ordinary differential equation. Otherwise, if I'm finding how the unknown function is changing with respect to at least two independent variables, then the equation becomes a partial differential equation, or PDE. Okay, so here are some examples. These equations are examples of ODEs, dy dt plus kt equals 10. Okay, so y is changing with respect to only one variable. Or if you like, there is no change with respect to another variable apart from that's one variable, one independent variable t. It's the same here. Dy is changing with respect to just x and x as well. There is no change with respect to another independent variable like, you know, t or some other variable. Okay, so these are ODEs. And these are examples of PDEs, all right? See, I'm looking at how u is changing with respect to x, as well as how it's changing with respect to y. So I have two independent variables here, all right? So this is a partial differential equation. The same here, how phi is changing with respect to x, as well as how it is changing with respect to y. And so we get a partial differential equation. All right. We also have another classification that has to do with, or if you like, a terminology that has to do with the order, all right? The order of a differential equation. So the order of a differential equation is the order of the highest derivative that appears in the equation, all right? For example, if I have an equation like this, I only have a first derivative, right? The x dt plus x is 0 is only a first derivative. This is a first derivative as well. And so these equations will be said to be first order. The order is 1, so it's first order differential equations. Whereas this equation here, you see, I'm finding the second derivative, right? Because I'm finding the second derivative here, the highest order here is 2. So the order of this differential equation will be 2. Second order, if you like. It's the same here. This is also second order. Note that the derivative here is first order, and I'm just raising it to the power 3. So it is not a third order derivative. So the order of the differential equation is actually 2, it's second order. Okay. Also, you will notice that sometimes in the differential equations, you have some constants that are appearing. So those constants are often called parameters or sometimes coefficients of the differential equation. So you can look at some of the previous equations. K in equation 1, for instance, is a parameter. A and B, if we go back to equation 4, you see there's an A here, there's a B here. These are parameters, okay? And they play a different role to the independent variables, all right? And you can see that there is no change with respect to A or respect to B, so you know that they are parameters and not independent variables. Okay? Okay, good. So these are just some terminologies I'm introducing. You know, the order of a differential equation, the difference between ODEs and PDEs, dependent variable, independent variable. So these are just terminologies that you need to learn before we get into doing other things about differential equations. Okay. More on the terminologies. A first order ODE is called explicit, all right? It's explicit if it can be written in this form, dy dx is equal to some function of x and y, all right? In this case, I'm able to separate out the rate of change or the change of the dependent variable respect to the independent variable, okay? If it cannot be written in this form, then it is an implicit ODE. Okay, so here's an example of a first order implicit. All right, you have a continuous function, and that function is a function of x, y, and dy dx. This is just an example. All right, in the next slide, I'll show you general cases of these. Okay, so if, for instance, here we can solve or isolate the dy dx, and then we'll have dy dx is equal to some stuff, then it becomes explicit. Otherwise, it's implicit. Okay. Good. So, for instance, the general form of an nth order, the order is n, the nth order implicit differential equation will be this. This is a general form of it. Okay. Where it is assumed that the equation holds for all values of x, right, in some interval, say x lying between a and b. This a and b could be infinity, from negative infinity to positive infinity, all right, or some interval. Now, if the highest order term can be isolated, right, and write dn dy dx dn is equal to some function of x, y, and other derivatives. If you can isolate the highest order term, then it becomes an explicit form of the differential equation. Okay, so that's the difference between explicit and then implicit differential equations. Okay, good. Now, what do we mean by the solution? The solution of a differential equation. We have explicit solutions and implicit solutions, okay? So for the explicit, a function phi of x, that when substituted for y in equation 7 is the explicit equation here, okay? If I put in y in this equation and I get the left-hand side being equal to the right-hand side, then that phi is a solution, okay? So that's what the definition is saying. If this, when I substitute for y in equation 7, satisfies the equation for all x in an interval I, it's called an explicit solution to the equation on the interval, okay? So here's a simple example of that. Show that this function, right, phi of x equals this, is an explicit solution to the linear equation this. This is an ODE, okay? Well, C there is a constant, it's just a constant. So basically you want to show that if I replace y here and with this function, all right, then the left-hand side will be equal to the right-hand side. If that happens, then this function is actually a solution to this equation, okay? So how do we do that? So let y be this, then all you do is find the derivative, right? We need to find the derivative with respect to x, and then add it to the function, right? And see whether our answer will be x. That's what we do, okay? So find dy dx, that's just equal to 1 minus c e to the negative x, right? So now if I take dy dx plus y, dy dx will be found to be this, 1 minus c e to the x. If I add y is a function. If I add it, note that the ones cancel out, the exponential terms cancel, and I'm left with x, and x is the right-hand side of the differential equation, which means that phi here is an explicit solution for all real x, all right, for all real values of x, okay? So that is how you verify that a given function is a solution to an ODE. Here's another example, okay? The function now is x squared minus 1 over x, or x to the negative 1. We want to show that this is a solution to this differential equation. So same procedure, let y be this, then dy dx will be equal to, I'm going to differentiate this. That gives me 2x plus x to the negative 2, right? I need to find the second derivative because of this. If I find the derivative of this, I'm going to get 2 minus 2x to the negative 3. So I can now take this minus, I take that, in place of y, I'm going to put the function and see whether I get 0, okay? Note that these expressions, all the expressions here, this thing here is 1 over x, right? They are defined for x not equal to 0. So we assume that x is not equal to 0. Otherwise, this guy will not be defined, right? Okay, so if you plug them into this, what do we get? We know this, so we put them in. The second derivative term is this, minus 2 over x squared. Y is this, the function given. So simplify this and you get this, the 2's cancel, the cubic terms cancel, and you end up with 0, which is the right-hand side of the equation, okay? So since this is true for all x not equal to 0, the function, this function here is an explicit solution to the differential equation on the real interval apart from 0, right? This is from negative infinity to 0, and then from 0 to infinity. Note that these are open intervals, so x equals 0 is excluded, all right? Okay, so that is how you verify. Here is another one. Well, this is well, it's interesting. We want to check whether the function, this function given here for x between negative 1 and infinity is a solution to this equation, differential equation. You follow the same procedure, find dy dx and see whether it's equal to the right-hand side, okay? So here we want to apply the fundamental theorem of calculus. So if you go back to your calculus, FTC, fundamental theorem of calculus, you You remember that if I have a function and I'm finding dy dx, then dy dx will be equal to, if I'm going to integrate this, because this is just the variable x, I can just remove the integral and replace the t here with my variable x, right? So look up the fundamental theorem of calculus. I have a video on integration and I tackled this, so you can take a look at that. So you have the square root of 1 plus x cubed, right? You just replace the t with this using the fundamental theorem. All right. So the derivative of y is the right-hand side. Therefore, y, this function is a solution, right, to the differential equation. Okay, awesome. Next, the next thing we want to look at is implicit solutions. We looked at explicit solution. Now, what is an implicit solution to a differential equation? A relation given by this, g of x, y equals 0, is said to be an implicit solution to the implicit differential equation, equation 6, on the interval I, if it defines one or more explicit solution on that interval I. Okay? We'll use example to illustrate what this actually means. So for instance, note that we want to verify that this is actually an implicit solution to the equation thus. Okay, note that this so-called solution, right, we haven't verified it. This solution is not in the form y is equal to something. You see, the y is not isolated. The y is all part of a function is equal to 0. So this right-hand side is what is represented by g here. Okay, as a function of x and y. Okay, so we want to verify that you can do that actually. You don't have to isolate y before you can check that it's a solution. You can actually do that. Check that this is a solution to this. How do you do that? Okay, so let's go to the next thing. First of all, we first have to assume, of course, that a solution exists. And we are confident that a solution exists based on a theorem called the implicit function theorem, which we're not going to actually tackle or talk about here. But you can assume that a solution exists and then go ahead to prove or show that this thing here satisfies. This is the solution, if you like. We'll verify that this thing here is an explicit solution to this differential equation. Okay, so to do that, what you do is that you take the expression, all right, it's here. Take this expression, differentiate both sides. You need to apply implicit differentiation, right? If you remember differentiation. Okay, so implicit differentiation. So find the derivative of both sides of it. So d dx of this side, that will be equal to, this will give me 1. This will be dy dx. I want to do this, I can pull out e to the x and then use the product rule to find the derivative of the exponents here, right? I differentiate x, I'll be left with y. I leave x, differentiate y, I get that. Okay, so I can rearrange this, multiply through by this, you get this. Pull out dy dx, and you have this expression plus this one, and then that guy. Okay. Because we differentiate this side, is equal to 0 as well. Now, if you look at this term here, what we have here, all of these, this is actually the differential equation given to us. This is the same as the equation we have. So we have shown that this expression, this thing here, is an implicit solution. Okay, so this is actually an implicit solution to the differential equation. Okay, so that is how you verify that an expression is an implicit solution to a given differential equation. Okay, good. So we are almost there. In the next couple of slides, what I'm going to do is that I'll walk you through a couple of fields or areas, if you like, that you can apply differential equations to, or areas where differential equations have been applied to. There are several of them. So I just picked a few as a way of motivation. Okay, so often in population models, right, or so-called logistic models, if P of T is the population of a species, all right, at a time T, then the growth of the population, right, like think of the mosquitoes that I used earlier on, or some other population, human population, right? The growth of the population is governed by the logistic model or differential equation given by this. K1 and K2 are constants, okay? You can rewrite this into this form, where A is another constant given by this. P1 is also a constant. And then this is our initial condition, all right? By the way, if you have a differential equation and then an initial condition is specified, it is called an initial value problem, okay? Initial value problem, IVP, okay? I didn't mention that when I was talking about terminologies, but when you see IVP, it is an initial value problem because you are given the initial value. So this is a differential equation you want to solve, and the initial value is given to you. The initial value helps you to get a unique solution to the differential equation. Okay, so this equation is often used to model the growth of a population, and it's called the logistic model. So this is one application of differential equations. Okay, now note that if the constant K2 here is 0, if this vanishes, this equation here, the P dt equals K1P, is the same simple equation I introduced earlier for the modeling the growth of or the decline of the population of mosquitoes. This is the same, where P now is the M that I used earlier on, okay? So when K2 is 0, this simplifies to a simpler model, and it's often called the Malthusian model, okay? It's a simple model because it doesn't capture other parameters of population growth. Okay, so this we are not solving this just to tell you that you can apply differential equations to population growth. That is the main point here. You can also apply it in electricity. For instance, if you want to know how an electric charge Q, okay, in a circuit, you have a circuit with an inductance, a resistance, and a capacitance, all right? And then you have a voltage, a source of voltage or electromotive force, okay? And then the charge, you have charges going through your circuit. How does the charge Q change with respect to time? Okay, is governed by this differential equation here, all right? Where E here is your, your voltage, electromotive force, if you like. And these are defined here. So this equation is often used. It's a typical example you will see in other textbooks. Okay, so, and also in psychology, I found this interesting that you can actually model, okay, the learning of a task by an individual learner. Let's say the individual is P, right? You can imagine that different people will learn things differently, right? A scientist, will learn about rocket science or about coding probably much faster than somebody with a background in history or some other field, right? So the individual is important, P. And then you also have, of course, the nature of the task that you want to learn, right? The nature also, right? There's a difference between learning how to cook and learning how to code, okay, for instance. And so in psychology, this differential equation is often used to model the learning of a task by an individual, where N here is the nature of the task, P here is the individual, Y here, of course, is the learner's skill level, all right, as a function of time. All right, in a year's time, how much have you learned? Okay, and then you try to quantify that. Or in 3 months' time, in 2 months' time. And so this can often be used to model that. Okay, good. And then this is now a partial differential equation that is often used to model options. Okay, the value V, right, of an option to buy or to sell a stock with price X at time T is governed by this differential equation, which is often called the Black-Scholes equation. All right. R here is a prevailing risk-free interest rate. Sigma squared here is a measure of the volatility of the investor's return on this particular stock. So those in financial math, financial stuff, economics, might find this interesting, right? So this is often used to model these kinds of stuff. Okay, good. Then on to our last sort of example, if you like, a motivation for differential equations. In this case, we move back to a predator-prey model, or so-called Lotka-Volterra system of equations. And in ecology, this can be used to study the dynamics of competing species. Okay, so if you have a predator, let's say a lion, represented by X2, that's a population of lions, and you have a prey. All right, the lion is preying on the zebra. Okay, and the population of the zebra is represented by X1. Okay, so just two of them. Then how is the dynamics? How is the population changing? Population of lions as against zebras. How is it changing as a function of time? You can often model that using these system of differential equations. All right. In this case, there are two of them, where A, B, C, and D here are some positive constants. Okay. I'll give a very simple cases of these. All right. We are not solving this. I'll give you a simple case of how you can often apply this. They are very interesting. Okay. So for instance, if there are no lions, so imagine a world of only lions and zebra, or a jungle where there are only lions and zebras. Lions are preying on the zebras. If, for instance, there are no lions, okay, and you have only zebras, what is going to happen? Okay, so if that's the case, then X2 is 0, which means if you go back to the system of equations, X2 is 0 means every term here was 0. So this equation goes out completely. This interaction term here goes to 0 as well because of the X2. And all you are left with is this simple equation here. Again, this is the equation that we met before on the group of population of mosquitoes. Okay, so you are just left with this, which you can easily solve. Okay, and then you get X1 of t is equal to this. K1 here is just a constant, and it's raised to the power e to the at. A here is a positive constant. What it means is that as t, right, this is a positive constant, what it means is that as t goes to infinity, the population of zebras goes to infinity as well. So the population of zebras increases without bound, which makes sense because there are no lions to prey on them. Okay, so the differential equations tells us that that is what happens. As t goes to infinity, X1 goes to infinity as well. So zebras will just multiply because there are no lions to eat them, if you like. Okay, so this is one extreme case. The other extreme case is that what happens if there are no zebras, all right? If there are no zebras, of course, X1 is equal to 0, all right? So you go to the differential equations, and then the first equation goes to 0 because everywhere you see X1 is 0. So this cancels out completely. This term also goes to 0 because of the X1 term, and you are left with this equation. If you solve this equation, you will end up with what? X2 as a function of time is equal to this. Because this c is a positive constant, you see that as t goes to infinity, all right, as t gets bigger and bigger, this term becomes smaller and smaller, and so x2 as a function of t goes to 0. Okay, so with time, the population of lions continuously diminish until they all die out. It goes to 0. And that makes sense as well because now you don't have zebras for the lions to prey on, and so they will eventually die. That is what the model is telling us. All right. So differential equations are very interesting because you can use it to actually model and try to understand different dynamics in real life and different fields. Okay. So that is why you want to learn differential equations. Okay, so I'll end with some exercises you can take a look at. The first set is basically on basic calculus. Okay, so basically try to find the derivative of these functions with respect to x. Do the same thing for these ones. Okay, so this is just to help you refresh your mind on some calculus stuff, derivatives. The next set is very similar. You want to evaluate these integrals again. if you go back to calculus 2, then you should remind yourself of how you do these things. You might need them, all right? Some of these in our course. And then finally, you want to take a look at this. We've done some examples of this, how to verify that a given function is actually a solution to the differential equations. For instance, you want to show that this guy is a solution to this differential equation. You want to do the same thing here, show that this guy here is a solution to that differential equation, and so on. Okay, so try your hands on these ones, and let me know if you have any challenges. Okay, so I wish you all the best. I will end the lecture here. And then my next one will go on to start studying first order differential equations. Okay, all the best.